lot of my background is actually in systems for computer graphics. So about half my group works on computer graphics. But what I'd like to talk about today is some of the newer work that we're doing on processing large numbers of images. So I'm particularly interested in helping the world process video with the ease that it now processes text or click streams or transactions. And I mean that for a variety of applications, whether it be for enabling the development of self-driving cars, whether it be for understanding what's on TV these days, or all the autonomy that might go into e-commerce, science, or even, in this future, even though it didn't go so well for Google the first time around, I do believe that there's probably going to be a camera on everybody's head in the not too distant future. So sometimes people ask me about what's the magnitude of data that I'm talking about, and I wouldn't, these are very, very loose estimates, but if I look forward about a decade, I have about 8 billion people in the world, and we're almost to 50% smartphone penetration already. So it's not all that insane to say that 70% of the people in the world are going to be running a smartphone. And let's say they're wearing that smartphone or a camera in the future 9 to 5 for their workday or a quarter of the workday. That's 1.5 billion video streams at any one time. If we look at vehicles, 2 billion cars, 8 cameras a car is probably a way underestimate. Let's say that autonomy brings us up from our current 2% load to 25%. That's another 4 billion video streams. I might be overestimating because autonomy might bring the total number of cars down. And all the market trends say that there'll be about 1 billion security cameras in the world. And let's say that they're always streaming. So we're talking about the world, if we move up to 8K video, being this 6 exapixel per second imager going forward. And so as someone who's built a lot of systems for computer graphics and making really fast rendering systems, I'm very interested in how do we architect the systems that will be able to make it much more productive and much more efficient to process that visual signal. So I started with a few applications, but I want to talk about some applications that some of my students have been looking at that have been driving some of the systems design decisions that we are making. Okay. So one example is trying to just do more with video. This is at the intersection of graphics and imaging. Maybe it's not VR, but there will probably be much, much richer forms of video that are captured with very complex rigs going forward. All of us have watched sports, and ESPN likes to spin the camera around. So even if the display is not necessarily in a headset, I can imagine a lot richer processing in the way we develop and distribute video. So this is an example from Facebook's 360 pipeline. They spend about 12.5 seconds per 32-core box to process a frame right now. That's pretty heavy. And it's so heavy because every single one of these 4K images goes through a 44-stage processing pipeline before the output comes out ready for a VR headset. So my collaborators, when I was back at CMU, this is not my student, are interested in capturing human social interactions. If we are going to have robots, they are going to need to interpret our facial expressions. They will need to interpret behaviors in a much more nuanced way than just that is an object over there, or that's a vehicle. So they built this dome, and this dome has 480 video cameras. The little black dots, I don't know if you can see, the little black dots in the dome are the video cameras. The thing that look like video cameras are these special HD cameras. So this dome generates this signal of video. There's 480 video streams. And this is about, if I remember correctly, it's 147 megapixel sensor video. And the reason why they're over measuring is they're very interested in recovering 3D at the level of facial expressions in conversations. So these guys, and this is work by one of my colleagues, is they're trying to figure out who's lying from the video. So they're playing a game of bluff. And you can imagine just simple interactions like in autonomy, like when I'm driving to work in the morning, I'm always looking to make eye contact with every other driver. And if I'm in a store, you can imagine a future Amazon Go store having cameras at this scale. So that's another example. And by the way, this using state-of-the-art NVIDIA or almost state-of-the-art NVIDIA GPUs, it took about 7 hours to perform this reconstruction for a 40-second segment. And last, with all the talk of TV news these days, we've become very interested in understanding more about what's on TV. So with Manish Agrawala, who's a faculty member just down the hall, and the Internet Archive, they've given us access to basically all the news. We've downloaded the last 3 years of MSNBC, Fox, and CNN. And we're interested in asking some questions about that. This is about 70,000 hours of video, and we're about to go to a whole decade. And yeah, we might be like doing things like detecting Anderson Cooper or trying to figure out where the panels are, but I'll talk a little bit later about some of the more nuanced things that we're trying to find in this data set. And so trying to find places where there's 3 heads on the screen and they're well aligned is not all that different computationally in like a self-driving car setting of I'd like to find all instances where there's a bicyclist and 2 pedestrians in front of a blue car. So you can imagine that we're pushing towards systems that allow me to more easily data mine these large video collections. So I want to talk about 3 things today. I want to talk very briefly about when my students started doing this, they were like, what system should I download to start running on 100,000 hours of video and use 10,000 cores on the cloud? And we found the current distributed systems infrastructure a little inadequate, just because people hadn't looked at this. So we've been building some systems that make it easier to process large amounts of video. So you can kind of think of as Spark or Hadoop, but tailored for video. We can run at scale now, but it costs us a lot of money. So we're doing some algorithm development with specialization and efficiency in mind. So not only are we building systems, we're trying to make the algorithms more efficient. And of course, we're interested in making sure that everything we rewrite compiles down to the latest ASICs, whether they be GPUs or multi-core CPUs, or hopefully in the future, these more exotic architectures that are emerging. So let me tell you a little bit about some of these things. So again, like a reminder, like I'm interested in building systems that process all kinds of video. It's both for synthesis, for creating things, and also for analyzing things. And by scale, what I mean is I would like to be able to provide my grad students or a data analyst or a data scientist a system that will not be constrained in the size of the database. It will not be constrained in the number of cores I can use if I have the money to use those cores. And those machines better be stackable with modern GPUs or other accelerators for this type of domain. Okay? And we looked around, and we thought we might just be able to modify Hadoop or MapReduce. And we just found that, outside the scope of this talk, that there were a huge host of requirements that video and image processing required us to hit that just were not well suited for the current frameworks. So we decided to build our own. And this is a system called Scanner, which, as you saw on the earlier slide, is available on GitHub to anybody today. We'd actually like to see some people start kicking the tires a little bit. And it behaves roughly like you'd expect. Scanner is a data store, which if you wanted to ingest 100,000 hours of video, you can do that with a few lines of Python code, and you get out a column store where the videos are represented as tables, and under the hood, the column store is representing everything in video-specific compressed form. And also, like you'd expect as a data analytics package, you can express those computations by building dataflow graphs in Python, much like you would see in TensorFlow or any of these modern machine learning frameworks, except we have a set of operators that are pretty useful for video. So I'm showing you a pipeline here that's a common thing that we might do, which is take every image off disk, downsample it for a DNN, drop a bunch of frames so that we only run on every 30th frame, evaluate a DNN on one of those frames, use it to seed an object tracker that propagates those labels to the rest of the frames. Those kinds of computations, right? And so Scanner, has a suite of data parallel operators that those of you that have done data analytics might be familiar with, your maps, reduces, folds, and things like that. But they just have a few tweaks for state management and state propagation through time that are very useful for video. And given those computations, we'll splat it for you out across a big parallel machine. That machine may have GPUs and CPUs. And so we make it easy for a data analyst to use this in a heterogeneous computing setting. Okay. So there's a few things that are some small wrinkles, and I'm going to be mainly results-oriented here, but some small wrinkles would be that in data analytics, most of the time, because of the compute density of these computations, we sample all over the place. And so this system is actually built along a notion of sparsity. So even though you have these data flow graphs, in this diagram, I'm showing you in the gray all the nodes or all the elements or images that I don't need to compute to satisfy a particular sparse sampling if I propagate those dependencies upstream. So the system at its core is only processing the images or the intermediates that it needs. And if you're doing something like I want these particular frames with these faces, or I want these every 5th frame, that actually matters a whole lot. And then the other thing we do is at the data store level, we have a lot of optimizations that are specific for video. So if you're sparsely sampling an H.264 encoded video stream, you kind of need to know where those keyframes are so you can avoid unnecessary I/O and unnecessary decode. And so we do a lot of those optimizations for you under the hood. Okay. And with that stuff, we've built a system that actually is fairly convenient, at least for us to use in the lab. And some folks at Intel and Facebook are starting to use it, at least experimentally right now as well. So here's an example of taking that 70,000 hours of video from the Internet Archive and just saying, I want to find all the faces in it, or I want to do human pose estimation on all 12 billion of those frames, and I want to use 4,000 cores in the cloud, or I want to use 200 GPUs in the cloud. So we can splat you out across the cloud, but we can also, and in graphics this really matters to me, if I care about doing something for a feature-length movie, I can get it back using that many machines. I can get it back in a few seconds using that big cluster. So we've applied this system to do a few things, like we've taken Facebook's Surround 360 pipeline using thousands of cores. That 12 seconds per frame is now a few frames per second. We took the other pipelines that I told you about that used to be 7 hours, and we've now gotten it down to that reconstruction is 25 minutes. So that allows those grad students to work a lot more quickly now. They don't have to wait overnight to get their results back. And we've just kind of kept going, right? We've decided to go grab a bunch of feature-length films, so we can get through 600 feature-length films in about an hour, or in a couple of hours now, on just like a single, just 4 boxes. And then going back to what I motivated this with, we were now ready to start running for real on the 70,000 hours. And we were really inspired by what Google did when Google scanned all the books. When Google scanned all the books, they wrote this paper about, hey, there's these amazing trends that have occurred over the decades of how language has changed. And these days, there's a lot of folks very interested in different types of visual media. Like, for example, the Genus Davis Institute at USC did a gender analysis of the top Hollywood films and sort of found what you'd largely expect, that there's about a 2-to-1 ratio of men to women in screen time, except in the horror genre of films. So we got our data, and we were like, maybe we can do some of the same things. So we downloaded this thing. It's about 20 terabytes. It's about 6 quadrillion pixels. And we've been starting to ask some questions about it. We have a whole bunch of questions that are related to both the visuals, the audio, and the text. And this is very ongoing stuff. So we're interested in questions like, well, what pictures of Barack Obama does Fox News choose to show versus MSNBC? Or are there particular ways that people dress after a major tragedy, or how does their language change? So those are some examples. But I'll go through a really, really simple example to just show you some of the stuff that we're hitting. Like, for example, let's repeat that experiment from USC. How much screen time do men and women receive? Right? So if I ran a state-of-the-art face detector on all of this data, it would cost me about $3 million on Google Compute Engine. Right? So that was out of the question. And so the first thing we started to do was sample the data. So the best way to sample for us was to say, you know what, there's all these camera shot changes in this video, right? And whenever you do a camera shot change, that's a pretty good stratum in sampling. So what we did is we actually touched every frame, and we segmented that video using color histograms into shots. And then we could sample once per shot, and then attribute that screen time for the entire shot. So that got me about a factor of 200, and now I'm down to about $15,000 to crank on the data set. And a lot of the work that we've done is fault tolerant, so I can use preemptible CPUs, and I got myself down to $3,000. And in fact, when we did this about a month ago, CPUs were, interestingly, the more cost-effective way than GPUs to actually do this inference analysis. So we did this, and guess what? We ended up with about the same gender ratio, about 2-to-1 of men to women. And we found this very interesting, but it was not flat across shows. And it's probably about what you'd expect. There are certain shows that are male-hosted, that are dominated largely by males. So the blue line here is the percent of screen time where there are people where it is male-dominated, or it's male. And then if you go look on the left, they're very female-hosted shows. And we confirmed this by saying, let's go detect the host. And so we didn't want to go label a bunch of hosts. So what we did is we actually just clustered all the data and found clusters, face clusters that happen to appear throughout the show, and those are the hosts. So so we know when hosts go on vacation. And so then when we take that out of the data, and if you look at the the solid blue line there, with the X's, if you actually take the host out of the equation, the non-hosts have a very uniform gender distribution across all the shows, which means that female anchor people, their shows are no more likely to bring on female guests or give screen time to females, which is similar to other studies that have been done in print media as well. So what you could be thinking, hey, Kayvon, some of the stuff that I just showed you, we could have gone with audio or other lower bandwidth forms of media to maybe get the same results. But now we're starting to go into more nuanced things, like how are people positioned around interviews? So we can get pose. We can ask questions like, well, what are people wearing? Here's a visualization of all the hosts subsampled across Fox and CNN. People end up kind of on average wearing about the same color of clothes on those two stations. There's been a lot of talk about, hey, I think Fox News hires a particular type of individual to be an anchor. Well, at least on preliminary results, it seems like there's just as many blondes on other stations as there are on Fox News. So this is a hair color assessment. But the people on Fox News, they do actually tend to wear dresses a lot more. And we don't know why, but you can imagine we're starting to dig into some of these things and starting to talk to historians and communications folks. So those are some of the things that we're trying to do, and let me just briefly summarize with some things that we're doing to address some of the efficiency issues. Like I said, I cannot have every time a grad student gets an idea, it's rough to pay $3,000 for it. And so if I was a machine learning person, which I am not, or I'm an AI person, which unfortunately I'm not, my aim would be to design the most general and intelligent model that I possibly could design. It should work in all the cases. That means I'm really onto something. But I'm interested in building some efficient systems. So, interpreting the contents of any one frame really requires a much smaller subset of the information in the world. And, many cameras, they don't see every possible thing in the world. They don't see every image on the internet. The camera on a street corner like this really only sees a very small fraction of images. Now, there might be motion in every frame, and if this was a busy time of day, there might be motion all over the frame. But man, that camera doesn't move. And, my car only sees it sees Palo Alto, and maybe every once in a while it sees San Francisco, but it sees a very limited distribution of the world's events. So we've been doing some stuff trying to design new networks that crank up performance by specialization. So one example is adding conditional execution back into these networks. And there's some other work in the community on this, but what we said is, we could have these really big, really accurate networks if we had some way to conditionally only execute a really small fraction of them at any one time. Right. And so we basically have been working on techniques to build case statements or if statements into networks so that even though you have the capacity to answer a lot of questions that you want to answer, you only light up a very small fraction of that capacity at any one time. So that's an example. And these dynamic networks, which are the blue dots on this graph, and the x-axis here is cost, the y-axis is accuracy, kind of take the exact same network topology, a really highly, a well-designed network like a mobile net, and move you up and to the left, just by being able to sort of condition on the instance at hand. Okay. And so now, and some stuff that we're working on now that we actually haven't put out even yet is, well, let's just take that to the extreme. Why even train a network that's general at all? Why don't we just train something that's really cheap but good enough for the next couple of seconds and just keep modifying our worldview, right? And that's something we're actually starting to see some success with. So here's some examples. On the right are kind of a state-of-the-art, expensive 4 frame per second detector on a modern high-end GPU. On the left is something that's about an order of magnitude cheaper. And it just is reasonably as good, arguably better, but it's because it's tiny, quick, and we're constantly re-updating what it knows. So this is an online training thing. And then last, I just want to say that I started this talk with building some systems. And I'll close with building some systems. We're also obviously very interested in compiling a lot of these computations efficiently to modern hardware, right? And this started in the space of not machine learning. It started in the space of image processing, where these image processing pipelines in your cameras and your smartphones are incredibly complex these days. And optimizing those codes is critically important, except nobody can do it. There's probably about 80 to 100 people at Google right now that write image processing code, and there are a very few number of them that are tasked to optimize this code. And by very few, I mean 2 or 3, and I know them. When they go on maternity leave or paternity leave, nothing happens for a while. This was actually a thing. So we worked with them to take their mental state of the world and encode it in a compiler. And so we built this auto-scheduler for these computation graphs. And so I'll close on my favorite graph in a paper. Usually you compare to prior work, but I feel very strongly in building systems that sort of are really useful to experts. So we went out and we got some experts, and we gave our compiler 3, this is our holdout set. We gave our compiler 3 algorithms that had never seen before, and we gave our developers at Google, our friends, 3 algorithms they hadn't seen before. And we asked them to tune their code. So the x-axis is them getting better, making the performance go up over minutes or hours. And the green line is sort of what the autoscheduler did in a few milliseconds. So we were happy that we were able to produce a graph that had a user study in a systems paper, and our users were our baselines in performance, which was kind of fun. And these are probably the 2 top developers in the world on these types of computations. Okay. So just to close up, so what I'm interested in is I'm interested in building out a stack to make it much more productive and much more efficient to to analyze large amounts of video. And we're doing that at the distributed systems level with Scanner. We're doing it by designing new algorithms that are performance-centric. And going forward, we're very interested in sort of moving up the expressibility stack. If you're interested in data mining these collections, what does it mean to have a query language? Or what does it mean to think about some of the common database abstractions in this context? So thanks for the time, and I will let Hector decide if we have time for questions. Yeah.
Okay, I think we'll get 2 questions. I'm kidding. Kayvon, thanks very much. So we do have time for some limited number of questions. I think we have one right here. And then back there.
Hi. Quick questions regarding to your systems.
Oh,
it's actually a batch-based system, if I'm correct.
Right, yeah.
We actually deployed about 80 cameras for a client last year on site, and it's actually streaming-based.
Great.
Is there any approach you suggest for streaming-based real-time analytics system?
Yeah, so there's a lot of work out there, really, on processing these things. This is one of the major projects. I think Hector mentioned this ISTC, the center we have with Intel across Stanford and CMU. The other major project is the streaming version of this, actually. So I think with streaming, you have a bunch of different concerns. You have multi-tenancy, which I don't have here. You have client-server distribution, even though I actually think that's a little bit overhyped from the academic perspective. I think you ship pixels or you don't ship pixels, one of the two. But yeah, I think that it's, probably most of the video in the world will be processed in a streaming fashion because you can't move it off the camera.
One of our major problems at the time was that we cannot upload to the cloud for 2 reasons. One is the bandwidth problem, that it's a remote offshore site. Yeah. And the other problem is that even if you trying to aggregate to a central server, the amount of bandwidth and ports and communications, you may easily overwhelm your network connections. It makes sense, and I think that you're going to push computation to the edge. We've made great strides in that. I think we're going to shrink from an algorithm standpoint, I believe there's 10 to 100x just from algorithms. So I think that if you combine what the various hardware vendors are doing with, at the hardware level with algorithmic innovation, like we've, not myself, but image classification, which may not be the most useful thing in the world, has had a 25x increase in accuracy per flop over the last 3.5 years. And so if you combine that with the system side of things, you are getting, every couple of years, you're getting another order of magnitude. And so I think that what you'll be able to do on the edge is pretty fantastic going forward.
I think we had another question over there.
From the video you showed us, did you recognize who was lying?
Oh, no, that's a hard problem. We were working with computer vision researchers on these tasks, and it became readily apparent that that's a hard problem. But they're very focused on building like a super accurate 3D capture of the whole human body, and that as the first step towards, if you have an accurate 3D model, you can then begin to figure out how to simplify or understand deviations for that model, which would then be steps towards that problem. But the first step in the research is basically measure the human body at a super high resolution.
There was a request to see the link on your previous slide.
Oh, where was that? That was here. Yeah, this is going to be a little rough, but we would like some feedback. It was right here, I think. Like, people are actively documenting today. Put it that way.
Okay. I just hope your friends are still friends after you showed that you could do better than them. They're going to get fired.
No, they work with us. They're co-authors. They're co-authors.
I'm kidding.
Yeah.
Okay. Thank you, Kayvon.